Good afternoon, everyone. Now we're going to discuss about DSP pipeline from sensor to decision. Today we are going to understand something very powerful, how a real world signal becomes a decision inside a digital system. Whenever we use a heart rate monitor, a small thermostat, a voice assistant, or even a mobile phone camera, there is a hidden mathematical pipeline working in the background. We usually see only the output, a number on a display, an alarm, a recognized voice, but we do not see the mathematical processing happening internally. In this session, we'll break that entire pipeline into simple and understandable mathematical steps. By the end of this lecture, you will clearly understand where the math happens, how analog signals are converted into digital numbers, how digital processing extracts useful information, and how systems finally take decisions. Now we're going to next. Now, why do we need a DSP pipeline? Hmm. Before we understanding the pipeline, we must understand the problem. The real world gives us analog signals. Temperature changes continuously with time. Sound changes continuously as air pressure varies. Light intensity changes continuously depending on brightness. Even heartbeat produces continuous electrical signals. These signals are not clean. They always contain noise. For example, when you speak into a microphone, background noise like fan sound or traffic noise also gets captured. Similarly, a temperature sensor may pick up electrical interference. But digital systems like microcontrollers and computers do not understand continuous signals. They understand numbers. They need discrete values, sample taken at specific time intervals. So there is a mismatch. You can see here real world and system differences. The real world is analog and continuous. The digital world is discrete and numerical. This mismatch is solved using the DSP pipeline. The pipeline converts messy real world signals into clean numerical data and finally into intelligent decisions. Okay. Now you can see the full flow chart, like how complete DSP pipeline. Okay. Complete journey from the real world to final decision. Everything begins with a physical quantity. For example, temperature, sound, pressure, light, or heartbeat. The sensor converts the physical quantity into an electrical signal. Then the signal is amplified and filtered in this signal conditioning stage. After conditioning, the continuous signal is sampled. Continuous becomes discrete. Then the sampled values are converted into digital numbers using an analog to digital converter. Now the signal exists as numbers inside a digital system. Digital signal processing is applied filtering, averaging, peak detection, feature extraction. Finally, the system compares the proceeded values with a threshold and makes a decision. If you observe carefully, the entire process is a chain of mathematical transformation. Physical quantity to sensor, sensor to signal conditioning, sampling, next quantization like edit analog to digital conversion, next digital signal processing, and next decision, lastly output. Okay. Next, we are going to see about stage one, sensor, mathematical model. Let us zoom into our first block, the sensor. The sensor converts a physical quantity into an electrical signal. Mathematically, we can model it as V of t equals to k multiplied by P of t. Here, P of t represents the physical quantity, k is the sensitivity of the sensor, V of t is the voltage output. For example, suppose a temperature sensor produces 10 millivolts per degree Celsius. If the temperature is 30 degrees Celsius, V of t equals 10 multiplied by 30, that is equal to 300 millivolts. So the sensor performs a linear scaling operation. The first mathematical transformation in the pipeline is multiplication. In some sensors, the relationship may not be perfectly linear. Sometimes it may be slightly non-linear, but for most practical applications, we approximate it as linear. At this stage, the signal is still continuous and analog. We have not yet converted into digital. You can see the flowchart, physical quantity is converted into sensor, sensor to voltage output, and this is called scaling. P of t is physical quantity, K is sensor sensitivity, and V of t is voltage output. Okay. Now we're going to stage two, signal conditioning. After the sensor, the signal is usually weak and noisy. So before converting it to digital, we prepare it. The first operation is amplification. V of t equals G multiplied by V of t. If the sensor output is 0.2 volts and gain is 5, the amplified signal becomes 1 volt. Sometimes the signal may swing negative, but ADC cannot accept negative voltage. So we add an offset. V of t equals V of t plus V offset. If signal varies from minus 1 volt to plus 1 volt, adding plus 1 volt shift to 0 to 2 volts. Next, remove noise using filtering. This is mathematically represented as convolution. V of t equals V of t convoluted with h of t. Convolution means weighted integration of the signal with a filter function. In simple terms, we smooth the signal. So, in signal conditioning, we perform multiplication, addition, and convolution. This stage is still analog. The math happens physically using resistors, capacitors, and operational amplifiers. You can see a block diagram, sensor output, amplifier, filter, conditioned signal, amplification, offset addition, analog filtering. Now we'll go to stage 3, sampling. Now we reach a important transformation, sampling. Until now, our signal was continuous in time. Sampling converts this continuous signal into discrete points. Mathematically, x of n equals v of n into v of nts. So, ts is the sampling interval. N is a sample index 0, 1, 2, 3, and so on. Suppose the sampling interval is 1 millisecond. At n equals to 0, we take values at time 0, and at n equal to 1, we take values at 1 millisecond. At n equal to 2, we take value at 2 milliseconds. Continuous becomes discrete. To avoid losing information, the sampling frequency must be at least twice the highest signal frequency. This is called Nyquist condition. After sampling, the signal is discrete in time but still analog in amplitude. Sampling alone does not make the signal digital. You can see here the diagram of how sampling is done. This is the analog wave, and this points is like discrete points, like at t equal to 1 the value, and 2 the value of the signal. Okay. Now we'll go to into stage 4, quantization and ADC, analog to digital conversion. Now the signal finally becomes digital. After sampling, the signal had discrete time values, but amplitude was still analog. Quantization converts each ample value into the nearest digital value. Mathematically, xq of n equals to q of x of n. If ADC resolution is 8 bits and range is 0 to 5 volts, there are 256 levels because 2 power 8 to 256, right? The step size delta equals 5 divided by 256. Suppose the sample value is 2.37 volts. The ADC rounds it to the nearest level. The difference between original and quantized value is called quantization error. E of n equal to x of n minus xq of n. Now the signal is discrete in time and discrete in amplitude. That means it is fully digital. Sampling made it discrete in time. Quantization made it discrete in amplitude. You can see here the diagram of how quantization is done. Quantization function. It's rounding of the function. It is an error. Quantization error. Like how it differs from the main level and quantization thing. Okay. Now we'll go to stage 5, digital signal processing. Now the full signal is fully digital. At this stage, the system performs mathematical operations on numbers. DSP is organized mathematical computation. A common operation is digital filtering. Y of n equals summation of d k multiplied k x of n minus k. We multiply current and past samples by coefficients and add them. This is called multiply accumulate. For example, if we average 3 samples, y of n equals 1 by 3 multiplied by x of n plus x of n minus 1 plus x of n minus 2. This smooths noise. Another operator is derivative. D of n equals x of n minus x of n minus 1. This detects sudden changes. In ECG, this helps detect peaks. We can also calculate RMS value to measure signal strength. All operations are addition, multiplication, subtraction, and comparison. There is no magic. Inside DSP processor, this is a special unit called max, multiply and accumulate. This stage transforms raw numbers into meaningful transformation. You can see here FIR filtering, derivative or difference change or detection, RMS or feature extraction. Now we'll go to next slide. Now we are going to discuss about stage 6, decision making. After decision processing, now we have meaningful values, but the system must decide what to do. Decision equals 1 if y of n greater than threshold, decision equals 0 otherwise. For example, if temperature is 42 degrees and threshold is 40 degrees, alarm turns on. In ECG, if peak crosses threshold, it is counted as a heartbeat. All complex systems ultimately reduce to simple comparisons. The pipeline ends with a logic. Mathematics transforms signals. Logic transforms them into actions. This is the whole process in this stage, process signal converted to like comparator will compare like this result and that result, and the decision will be made, and output we can able to see. And this is the function. Okay, down there are examples like temperature is greater than 40 degrees, alarm on, peak detected, heartbeat, sound level high, then trigger system. Next. Now, in this slide, we are going to see the complete mathematical journey from sensor to decision. Let us see the entire journey in one chain. We start with the physical quantity P of t. The sensor scales it. P of t equals Kp of t. Sampling converts it into x of n. Quantization converts into xq of n. DSP applies filtering and mathematical operation to produce y of n. Finally, the system compares and makes a decision. Okay. The DSP pipeline is nothing but a structured mathematical transformation of real world signals into intelligent decisions. Whenever you use a smart device, remember behind it lies this pipeline: multiplication, addition, sampling, comparison. From sensor to decision, that is the power of digital signal processing. Thank you.